AP Physics 1, Workbook, Unit 4, Work and Energy, Activity L, the sign of work. Please read along with me, pause and rewind as necessary. Here's the scenario. Two identical tracks having significant friction are shown in the diagram. Identical blocks 1 and 2 are each set on the leftmost part of one of the tracks and given an initial speed v0, period. Block 1 goes up its track and block 2 goes down its track as shown. Block 1 will come to a stop after traveling length L1, and block 2 will travel distance L2 before coming to a stop. Predict. Part A. If students perform this experiment, which block would travel farther on its track before coming to rest? Explain your predictions, reasoning in terms of energy transformations. Okay, so we're going to take a prediction approach at first. We're going to look at some sample data, and then we're going to go step by step through a derivation to mathematically see why L2 will go farther. Let's begin. In both cases, the initial speed of the block is the same, comma, which means that in both cases, the initial kinetic energy of the block is the same. If the system is considered to be only the block, then the energy removed by the net external force on the block, which would be the frictional force, also has to be the same. This is because the initial energies are equal, and they will come to rest when the box has zero mechanical energy. For block 1, the frictional force and gravitational force are both in the negative direction, pointing down the hill. But for block 2, they are pointing in opposite directions. The component mg sine theta will go downhill and friction will go uphill. We'll see this derivation play out a little bit later on. Part A2. Through experimentation, students measure values for L1 and L2 shown in the table. Do the results in your experiment agree with the predictions made? Well, our prediction is that L2 going downhill is going to go a little farther than L1. So L1 kind of makes sense. If you go look at the picture for it, you have, and I'm speaking in terms of a Newton's law approach, okay, but we're going to talk about it from an energy approach shortly. You've got mg sine pointing downhill, and you have friction going downhill. You have two opposing forces to the slowing down or acceleration of block 1 as it goes up the hill. Whereas block 2, on the other hand, as it goes downhill, it's going to have mg sine theta going downhill and friction going uphill. It's going to have less opposing force. That means it's going to have a greater acceleration, which means it's going to essentially go farther. So from a Newton's law approach, right, we can see why L2 ends up going a little farther. But we're going to talk about it from a work energy principle point of view, which is very similar to Newton's second law, which is why the whole thing works so well together. Okay, so what did we establish? Well, L2 is longer. And look at your values for L2. They're all just about larger than L1. So I would say yes. Now the exception, of course, is made right here with this third trial. Okay, and let's talk about that in our reasoning. Looking at the data and not at the average, we can see that the values for L1 are almost always less than L2. Obviously, there is an error right here in the third trial where the measurement of L1 is almost 10 times larger than any other trial. That right there would be an outlier. And outliers are not to be considered as part of the average. So that's why the average looks so much higher. If you take this out and average those remaining 4 values, you can see the average for L1 is consistently lower than the average for L2. Part B, quantitative reasoning. Suppose that the coefficient of kinetic friction in both cases is mu, and each block has mass m, and both inclines are angle theta. Derive equations for in terms of v naught, m, mu, theta, and g, identifying whether you've used forces and motion principles or conservation energy in your derivation. So it looks like they're giving a choice. They're giving a choice in terms of whether you can use Newton's laws or use conservation of energy principles. Well, since this is an energy unit, I want to make sure we practice using energy principles. Okay, I already kind of did a little bit of a prediction with forces in motion and Newton's laws, but let's take a look at it a different way. Okay, to begin with, start with a fundamental principle, the work energy principle, which states that the net work is equal to a change in energy. The work done by a net external force will be equal to the change in kinetic energy. Okay, so what we're going to do is we're going to change. We know that the net work is force times distance, so we're going to change that into net force times distance times the cosine of the angle equals a change in kinetic energy specifically. So that's the energy that's changing. The two external forces in this case are friction and the component of the weight, little typo there, which are both exerted in the same direction. They both point in the opposite direction of the block, so the displacement will be the displacement to theta in the work equation is 180 degrees. Okay, so how does this play out? The net force, we're going to substitute for net force. So the net force would be friction and mg sine. Those are both of the forces that point downhill when the object is going uphill, when block 1 is going uphill, times d, distance d would be length L, times the cosine of 180, we're substituting for theta now, equals delta k. Trying to squeeze all that in there. Cosine of 180 is equal to negative 1. And so what we end up with is negative friction plus mg sine times L. That's the work, that's the net work on the left side of the equation, equals 1/2 m, because that's common, and then the change, basically a change in kinetic energy can be written as 1/2 mv squared minus 1/2 mv naught squared, and we're just factoring out a 1/2 m, so you understand where this is going. So v squared minus v naught squared, like that. Distribute the negatives, and we get negative friction minus mg sine theta, and I'm going to keep the parentheses there because L is also distributed out. Mg sine theta times L equals 1/2 mv naught squared. And the reason why is that, and it's going to be negative, because 1/2 mv squared is going to be 0. The block's going to come to rest. Friction is equal to mu times the normal force. So we're going to go ahead and normal force. So friction is mu times normal force, and normal force is mg cosine theta. So we're going to make that substitution right there. So all of this is going to now become, and you'll notice that, look at the negatives here. The negative, negative, and negative terms, once I distribute the L, if I factor out the negative terms will cancel on both sides. So that's kind of nice. So I suppose maybe even distributing the negatives probably wasn't necessary in the previous step. So I think what I'm going to say instead, let's keep the negative term out, plus mg sine times L. equals negative 1/2 mv naught squared. So I said instead of distributing the negative sign, I would say let's go ahead and set 1/2 mv squared equal to 0 because the block comes to rest. Right, and then the negatives will cancel like that. Okay, so now we're going to substitute for friction. So we get mu mg cosine theta plus mg sine theta. So that's substituting for friction. All of this is times L, and that's going to equal 1/2 mv naught squared. Solve for L. So to solve for L, we're going to simply divide by the by everything in parentheses. So L1 is equal to mv naught squared over, the 2 is already down there, 2 times the quantity mu mg cosine theta plus mg sine theta. There we go. Okay, let's solve for L2. Again, we're going to start with fundamental principle. Work is equal to a change in energy. And we're going to treat the block as the object, so the work done is equal to the net external force times distance cosine theta, and that's equal to an object's change in kinetic energy. Okay, now in this case, the net external force, you don't have 2 of them going in the same direction. Instead, the net external force would be mg sine theta going downhill, that's the causing force, minus friction times L cosine of 180 equals one half mv squared minus 1/2 mv naught squared. Okay, redistributing the negative signs, we get mg sine minus friction times L equals 1/2 mv naught squared. I guess we distributed the negative signs here, which means we're going to put this down here. And this would be substituting for friction. So we get mg sine theta minus mu mg cosine theta, that would be friction, times L2 equals 1/2 mv naught squared. And again, go ahead and solve for L2. And L2 would be mv naught squared over 2 times the quantity of mg sine theta minus mu mg cosine theta. Okay, now in part C, right, it says explain how your answers in part B support your experimental determination. Well, here's basically what's going on. If you look mathematically, the denominator, when you're subtracting terms, your denominator is going to be lower, which means the overall length is going to be greater. Whereas here, when you're adding 2 terms, your denominator is going to be greater. Therefore, your whole value for L1 is going to be lower. So the denominator of the expression L2 is always going to be smaller than L1. Therefore, the value of L2 will be larger. This matches the experiment because L2 data points, ignoring the outliers, ignoring the step 3 outlier, are larger than that for L1.